Hello student, welcome to my channel Learn Physics. Today I will be discussing the exemplar MCQ, short question and numerical of chapter 1 NCERT volume 1. I have already uploaded the one short video of electric charges and field. This video will be extremely helpful for you for preparation of 10 plus 2 exam, NEET, main and advanced. I hope this video will also be beneficial for you. Please like, share and comment on it. If you are new, please subscribe my channel to get the new videos for your next exam 10 plus 2, NEET, main and advanced. Okay, now let's start. Now look at this question 1.1. Look at this figure. This is the 1.1. Two positive charges. This is the Q2 and this is the Q3 fixed on the y-axis exerted net electric force in the positive x direction on the charge Q1 fixed along the x-axis. Look at this. This Q1 charge experiences a force towards the positive direction of x-axis. So this charge must be negative, because this charge attracted by this charge also attracted by this. Okay, so resultant force is directed along this direction. Okay, now look at this. If a positive charge Q is added at x equals to 0, look at this. A positive charge added here. If positive charge added here, look at this. It attracted more force towards this direction. Okay, now what are the options? Look at this. Shall increase along the positive direction of x-axis. Okay, this option correct. Okay, now numerical 1.2. A point positive charge is brought near an isolated conducting sphere. The electric field is best given by. When an isolated conducting sphere, suppose this sphere, is brought here, look at this, due to electrostatic induction, negative charge induced here. Okay, this is the bound induced charge and positive charge induced here. Okay, no problem. So look at this. According to properties of lines of force, the lines of force originates from the positive charge and terminates at the negative charge. So look at this. Here lines of force terminates perpendicular to this point. Now here lines of force originate from this perpendicularly. So this figure is the correct representation of the field. Okay, now look at this. This portion is correct, but this portion is not correct, because the lines of force does not ends at positive charge. Look at this. Look at this. Here lines of force are not normal to the surface. Here lines of force not normal to the surface, and the and the lines of force ends at the positive charge. So this is false. Okay. Now look at this question number 1.3. Electric flux through the surface. Look at this. This is the surface. This is the charge Q, surface, charge Q, surface S, charge Q, surface S. So electric flux phi is equal to, this is the Q by epsilon naught. A charge enclosed by each surface is same. So flux is also same. So look at this. The option D is correct. Same for all the figures. Okay, next. Now question number 1.4. 5 charges Q1, Q2, Q3, Q4 and Q5 are fixed at their positions as shown. Look at this. This is the Q1, this is the Q2, this is the Q3, and this is the Q5. Okay. And look at this. This is the Gaussian surface. So charge inside the Gaussian surface is Q2 and Q4. And Q1, Q3, Q4 outside the Gaussian surface. Okay. Now look at these statements are electric field on the LHS of the above equation will have a contribution from Q1, Q5, Q3. No. Electric field is the contribution of all charges present in it. Okay, so this is the wrong. Now option B, E on the LHS of the above equation will have the contribution from all charges. Okay, this up to this correct. While Q on the RHS will have the contribution from charge enclosed by the Gaussian surface. So look at this. This is the Q2 and Q4. So option B is correct. Okay, understood? Next. Now look at this question number 1.5. In the figure 1.5, look at this. In the figure 1.5, shows the electric field lines in which the electric dipole P is placed as shown in figure. Look at this, the electric dipole. This is the minus Q charge, this is the Q charge. Okay. And look at this, the lines of force are diverging in nature. So electric field at this point, suppose this is the E1 greater than electric field at this point E2. Okay, no problem, because number of lines of force crossing per unit area normally represents the magnitude of electric field. So look at this, here lines of force are closer, here lines of force are far away. That is why E1 greater than E2. Okay. Now look at this. Which of the following statements are correct? Look at this. The charge minus Q1 experiences force along this direction. So this is the QE1. And Q2 experiences the force this, and plus Q experiences the force. This is the QE2. Obviously QE1 greater than QE2. Okay. So net force on the electric dipole directed towards left. Okay, no problem. Now option, the dipole will not experience any force. No. It happens in uniform electric field. Now B, the dipole will experience force towards right. No, towards left. Okay, the dipole will experience a force towards left. Okay, understood? Next. Now question number 1.6. If point charge plus Q is placed at a distance d from an isolated conducting plane, the field at the point P on the other side of the plane is. Now look at this. This is the conducting plane. Okay. Now this is a point charge. Look at this. This is the plus charge. So induction takes place in this side. This is the negative charge. And in this side, this is the positive charge. Okay. So look at this. The field lines is directed away from the positive charge. So look at this. Field line is directed away from the positive charge. Now look at this. Now the field at the point P of the other side of the plane is directed perpendicular to the plane and away from the plane. So option A is correct. Okay. Now question number 1.7. A hemisphere is uniformly charged positively. The electric field at a point on a diameter away from the center is directed. Look at this. Look at this. Suppose this is a base of a hemisphere. Look at this. Suppose this is the hemispherical surface. Now the electric due to charge on its surface on the hemisphere, the field is directed always radially outward. Okay, the field is directed radially outward. So obviously this force is always perpendicular to the diameter. Okay, so look at this, option A is correct. because the field along parallel to the diameter cancel out. Okay. Now question 1.8. If surface integral E vector dot ds vector is 0 over the surface, then look at this, the electric field inside the surface and it is 0. Look at this, electric field may be parallel to the surface. Now the direction of electric field may be parallel to the surface. Okay. The electric field inside the surface is necessarily uniform. No, 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 no. The number of flux lines entering the surface must be equal to the number of flux lines leaving the surface. As net flux 0, so flux entering into the surface equal to flux leaving from the surface. All the charges must necessarily be outside the surface. As flux 0, so net charge q by epsilon naught 0, so no charge present inside the Gaussian surface. Okay. So look at this, option C and option D are correct. Now question number 1.9. The electric field at a point is always continuous. No, no, no. Continuous if there is no charge at that point. Okay. Now discontinuous only if there is a negative charge at that point. No, 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 no. The discontinuous if both positive and negative charge present at that point. So C is not correct. Discontinuous if there is a charge at that point. Okay, this is the correct and this is the correct. Okay. Now question number 10. If there were only one type of charge in the universe, then look at this, E vector dot ds vector not equal to 0 for any surface. No, no, no. If the surface contains the charge q, then E vector dot ds vector not 0. Otherwise, E vector dot ds vector equal to 0. Look at this. E vector dot ds vector is 0 if the charge is outside the surface. Okay, this is the correct. Now see, the surface integral E vector dot ds vector could not be defined. No, no, no. It can be defined. And look at this D. The surface integral E vector dot ds vector equal to q by epsilon if charge of magnitude q were inside the surface. So this is also correct. Therefore, option B and D are correct. No problem. Now question number 1.1. Consider a region inside which there are various types of charges, but the total charge is 0. Total charge 0, that means equal amount of positive and negative charge present here. So electric dipole is produced. Now at point outside the region, the electric field is necessarily 0. No, 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 no. Electric field due to a dipole is directly proportional to 1 by r cube. Okay. The electric field is due to the dipole moment of the charge distribution only. No, 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 no. The dominant electric field proportional to 1 by r cube. Okay, this is the correct. The work done to move a charged particle along a closed path away from the region will be 0. Look, the work done to move a charged particle along a closed path away from the region will be 0. As electric field is conservative system, so work done in a closed path is always 0. So option C and D are correct. Okay. Now look at this question number 1.1. Refer to the arrangement of charges in figure 1.6. Look at this. This is the 1.6. Look at this. This is the charge Q at the center of the spherical region. And this is the charge minus 2Q at a distance r by 2 from Q. And charge 5Q at a distance r from the surface. of the spherical region. Okay, now option A, the total flux through the surface of the sphere is minus q by epsilon naught. Now look at this, the charge enclosed by the Gaussian surface q minus 2q, that is minus q. So look at this option is correct. Okay, now B, the field on the surface of the sphere is minus q by 4 pi epsilon naught r square. No, 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 no. Field depends on charge. Now field depends on charge. Now field on the surface depends on the combination of charge q minus 2q, and this is the 5q. So this is not correct. Okay. The flux through the surface of the sphere due to 5q charge is 0. Okay, as 5q charge is outside the Gaussian surface, so flux due to 5q charge is 0. Okay, now option D. The field on the surface of the sphere is due to minus 2q is same everywhere. No, 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 no. If the minus 2q charge is placed at the center, then the field becomes uniform over the surface. As it is far away from the center, so this not happens. Okay, so A and C options are correct. Okay, now look at this question number 1.13. If positive charge q is uniformly distributed along a circular ring of radius r. Okay, look at this circular ring of radius r. A small test charge q is placed at the center of the ring. If q greater than 0, that is q is positive, okay, and is displaced away from the center, then the center in the plane of the ring, it will push back towards the center. Okay, look at this. If the charge slightly moves, if the charge slightly moves along this direction, then the repulsive force in this direction increases, and the charge again back to the center. Okay, so this option is correct. If q less than 0, that is charge q is negative and is displaced away from the center in the plane of the ring, it will never return to the center. Yes, look at this. If the charge minus q is displaced here, it is attracted by this charge with more force, so it moves away from the center. So this option also correct. If q less than 0, that is negative charge, it will perform SHM for small displacement along the axis. Yes, here force directly proportional to minus x, so it executes SHM along the axis of the ring. Okay, so C also correct. If q at the center of the ring is in unstable equilibrium within the plane of the ring for q greater than 0. No, no, no. It becomes a stable equilibrium. Now look at this very short answer question. An arbitrary surface encloses a dipole. What is the electric flux through this surface? Look at this. Suppose this is the arbitrary surface. Here, this is the minus q and plus q charge present. So net charge 0. So flux phi equals to q by epsilon naught, that is 0 by epsilon naught equal to 0. Okay. Now look at this question 1.15. A metallic spherical shell has inner radius r1, outer radius r2. A charge q is placed at the center of the spherical cavity. What will be the surface charge density on the inner surface and on the outer surface? So look at this. This is the inner surface. This is the outer surface. Charge placed q at the center. So look at this negative minus. So minus q charge induced at the surface of inner surface. So minus q charge is induced at the inner surface, and plus q charge is induced at the outer surface. Okay, the magnitude of charge both inner and outer surface is same. So this is the minus q charge, and this is the plus q charge. Now the radius of the inner spherical shell, this is the r1. So surface density of charge sigma 1, this is the minus q divided by 4 pi, this is the r1 square. And surface density of charge in the outer region, this is the q divided by 4 pi r2 square. Okay, no problem. Now question number 1.6. The dimensions of an atom are of the order of angstrom. Thus, there must be a large electric field between the protons and electron. Why then the electrostatic field inside the conductor is zero? Look at this, electric field is produced due to excess charge. As excess charge in the atom is zero, so no electric field is produced within the metallic conductor. Okay. Now look at this question number 1.17. If the total charge enclosed by the surface is zero, does it imply that the electric field everywhere on the surface is zero? No, 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 no. Electric field may be parallel to the surface of the conductor. Now, conversely, if electric field everywhere on the surface is zero, look at this, it electric field zero, so E vector dot ds vector, this equal to zero, so no charge present inside the surface. Okay. Now question number 1.18. Sketch the electric field lines for a uniformly charged hollow cylinder shown in figure 1.8. Look at this, the electric field is directed away from the positive charge. So look at this, this is the direction of electric field. Okay. Now look at this, this is the direction of electric field, this is the direction of electric field. Now look at this, in the boundary, the electric field directed along this direction, electric field directed along this direction, electric field directed along this direction. Here electric field directed along this direction, and this direction. Okay. Next. Now question 1.19. What will be the total flux through the faces of the cube with side of the length A and the charge Q is placed? Look at this, A means this point at the corner of the cube. Here Q charge placed here. Look at this. Now look at this. Look at this. This is the cube. Suppose this is the cube. Charge is placed here. This point. This point. So to bring the charge at the center, 8 cubes are required. Look at this. 1, 2, 3, 4. Now look at this. The charge becomes at the top surface of the center. To bring it the center, look at this, another 4 cubes are required. Look at this, another 4 cubes are required. So look at this. Now total flux is Q by epsilon naught. So the flux on each cube, this is the Q by 8 epsilon naught. Okay. Now look at this. So look at this. This is the Q by 8 epsilon naught. Look at this. B means, look at this, at this point, midpoint of the edge of the cube. Look at this. Here charge is placed at this point. Now now 4. Now look at this, the 4 now charge at this point. So this be now, so 4 cubes required to bring the charge at the center. Look at this, 4 cubes are required to bring the charge at the center. So look at this, here flux becomes Q by, this is the 4 epsilon naught on each cube. Look at this. Next, center of the face of the cube. Look at this charge here. So bring the charge at the center, another cube is required. So total flux in the 2 cube is Q by epsilon naught. So flux on each cube, this is the Q by 2 epsilon. Now the point D, midpoint of B and C. Look at this, B and C. Look at this, if the charge is placed here, so only 2 cubes are required to bring the charge at center. So look at this, here also Q by 2 epsilon. No problem. Okay. Now, short answer question 1.20. A Paisa coin is made of aluminum and magnesium alloy and weighs 0.75 gram. It has a square shape and its diagonal is 17 millimeter. It is electrically neutral and contains equal amount of positive and negative charges. Treating the Paisa coins made up of only aluminum, find the magnitude of equal number of positive and negative charges. What conclusion do you draw from this magnitude? Okay. Now to calculate the magnitude of positive and negative charge in the coin, we have to calculate the number of mole. Look at this here, number of mole. This is the 0.75 in divided by 27 as for aluminum. So total number of molecules, so total number of atom is equal to, look at this is a 0.75 by 27 into 6.023 is the total number, 6.023 into 10 to the power 23 is the total number of atom present in the coin. Now for aluminum, the number of electron and number of proton is 13. So total number of electron into 13. So charge of electron, this is the 1.6 into 10 to the power minus 19. So this is the total amount of negative charge and positive charge. So look at this. If you calculate this, we get, look at this, this is the 0.75 by 27 into, this is the 6 into 13 into 1.6 into 10 to the power 4. This coulomb. So this amount of negative and positive charge present in the coin. Okay. Now look at this question number 1.22. Figure 10. Look at this figure 10. Represents a crystal unit of cesium chloride CaCl. The cesium atom represented by the open circle. Look at this. This is the open circle. This is the cesium atom. This is the cesium atom. This is the cesium atom. Cesium atom. Okay. Are situated at the corners of the cube of side 0.04 nanometer. Whereas the Cl atom situated at the center of the cube. Look at this. This is the Cl atom. Okay. The Cs atom are deficient in one electron while Cl atom carries an excess electron. So this is the positive charge, 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 this is the positive charge. Okay. And this is the negative charge. No problem. What is the net electric field on the Cl atom due to Cs atoms? Look at this. As 8 Cs atoms are symmetrically situated around Cl atom, so net electric field at the position of Cl atom E equal to 0. Now 2. Suppose the Cs atom at the one corner A is missing. Look at this. The Cs atom at this corner is absent. Okay. What is the net force now on the Cl atom due to 7 remaining Cs atom? Look at this. This is the A and the diametrically opposite point C. This positive charge exert a force on Cl atom. Look at this. And this force, look at this, exert a force along this direction. The other Cs atom, the force exerted by other Cs atom cancel one by other situated at the two diametrically opposite point. So now net force, look at this force F equal to, this is the E into E divided by 4 pi epsilon naught into root 3 into 0.4 by 2 into 10 to the power minus 9 whole square. Okay. So look at this, the value are, look at this is the 9 into 10 to the power 9. This is the 1.6 into 10 to the power minus 19 whole square. Divide by, look at this is the 3 by 4 into 10 to the power minus 18. Okay. Look at this is the 10 to the power minus 38. and this is the 10 to the power 18, so 10 to the power minus 20, 10 to the power minus 20 and 10 to the power 10, so 10 to the power minus 11. So look at this and this is cancel out, this is the 3, so this is the 12 into 2.56 into 10 to the power minus 11 Newton is the force on chlorine atom. Okay. Now look at this question number 23. Two charges Q and minus 3Q are placed fixed on the x-axis. Look at this. This is the x-axis. Okay. Now here charge. Look at this. This is the minus 3Q and this charge Q is placed on it. Okay. D is the distance between them. Look at this. D is the distance between them. Okay. Where should the third charge 2Q be placed such that it will not experience any force? Look at this. If the electric field due to this charge and this charge is 0 at this point, then if we place 2Q charge at this point, that is this point, then force on 2Q is 0. Suppose this distance is x. So look at this, the electric field 0, so Q divided by 4 pi x square equals to 3Q divided by, this is the 4 pi d plus x whole square. Now d 4 pi epsilon naught, 4 pi epsilon naught, this and this cancel out, this and this cancel out. So look at this, 1 by x whole square equals to root 3 divided by d plus x whole square. Now just calculate x from this equation. So look at this, this is the 1 by x equals to root 3 divided by d plus x. Okay. So look at this, this is the x into root 3 equals to, look at this, d plus x. Therefore x equals to root 3 minus 1 into d. So x equals to, this is the d by root 3 minus 1 from the charge Q. Okay. Now question number 1.24. Look at this, in this figure, charge A, charge B, charge C present. Okay. So look at this, electric field line around the 3-point charges ABC are given. We know the number of lines of force originate from a charge or terminates at a charge represents the magnitude of charge. Look at this, at the point C, the number of lines of force originate from here mode. So C is positive charge and its magnitude is greater than charge B and charge A. Okay. Now again look at this, the lines of force is also closer at B than A. So charge B greater than charge A. Okay. So look at this, which charge is positive? Look at this here. Look at this, lines of force originate from C, lines of force originates from A. So look at this, C and A are positive charge. Which charges are largest magnitude? Look at this, C charge, that is QC is of largest magnitude because number of lines of force originates from C is much greater than the B and A. Now in which region or regions of the picture would the electric field be 0? Justify your answer. Look at this, between A and C, if a line is drawn, the electric field 0, suppose this point, because magnitude of charge A is less than magnitude of charge C, so electric field 0 at this point. And look at this, between C and B, the electric field is 0 somewhere here, and between B and A, the electric field 0 somewhere at this point. Okay. So look at this, so near A, yes. Now look at this question number 1.25. 5 charges Q each are placed at the corner of a regular pentagon of side A. Look at this is the regular pentagon of side A. Okay. What will be the electric field at O at the center of the pentagon? Look at this here, Q charge, Q charge, Q charge, Q charge, Q charge. So electric field at O is 0. What will be the electric field at O if the charge from one corner is removed? Look at this, charge from one corner is removed, then electric field due to other charges is same as produced by the electric field discharge. So look at this is the q by 4 pi epsilon naught r square and directed to this point. Okay. What will be the electric field at O if the charge q at A is replaced by minus q? Look at this. Here charge present. Here charge q is placed by minus q. Look at this. The electric field due to discharge, 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 and discharge is directed towards A. Okay. And electric field due to minus q charge is also directed towards A. So net electric field at O is the 2q divided by 4 pi epsilon naught r square directed along the direction of OA. Okay. Now question 1.27. Consider a sphere of radius r with charge density distributed as rho r equal to kr inside the sphere and 0 outside the sphere. Find the electric field at all points r. Look at this electric field on all points of r. Look at this. This is the spherical region. Okay. So electric field at a distance r. This is the surface integral E vector dot ds vector. This equal to integration of rho into dv divided by 1 by epsilon. Now look at this here E into this is the 2 pi, this is E into 4 pi r square. Okay. And this is the 1 by epsilon naught. Look at this integration of dv. This is the 4 pi r square dr into rho is the kr from 0 to r. So look at this E into this is the 4 pi r square. Now r square and r. So r cube. The integration of r cube is the r to the power 4. So look at this. This is the 4 pi. This is the r to the power 4 k by 4 epsilon naught. Now look at this 4 pi. This is the 4 pi cancel out. So E equal to this is the k and this is the r square by 4 epsilon. Okay. This is the electric field at a distance smaller within the sphere. So E proportionate, look at this, this is the r square. Okay. Now B. Suppose the total charge on the sphere is 2E. If total charge 2E, so look at this 2E equal to, this is the integration of rho into dv from 0 to r. Now look at this is the 0 to r. Look at this rho is the kr and this is the 4 pi r square dr. So look at this becomes 4 pi, this is the k and this is the r to the power 4 by 4. Okay, this equal to 2e. Now so k becomes, look at this, so k becomes, look at this, k becomes, this is this and this cancel out. So k becomes, this is the 2e by pi r to the power 4. This is the magnitude of k. Okay, no problem. Now where can two protons be embedded such that the force on each of them is 0? Look at this. Now net force on the proton is electrostatic repulsive force and look at this is the force due to electrostatic field. So force due to electrostatic field, look at this is the E into E. Okay, and this equal to this is the E into E divided by 4 pi epsilon naught. This is the 2r whole square. Okay. Now electric field E equal to this is the k, this is the r square by 4 epsilon. Okay, no problem. And look at this is the, look at this is the 2 this is the E, this is the E square, divided by, look at this is the 4 pi epsilon naught into 4r square. Now this and this cancel out. If we put the value of k, look at this. So look at this is the E into r square and k is the 2e divided by, this is the pi r to the power 4 into epsilon naught equal to E square by 4 pi, this is the epsilon naught into r square. Look at this, E and E square cancel out, pi cancel out, epsilon naught also cancel out. So look at this is the 8 r to the power 4 equals to capital R to the power 4. So r equals to, this is the capital R by 8 to the power 1/4. So distance of proton from the center of the spherical region is r by 8 to the power 1/4. Okay. Now look at this question number 1.28. Two fixed identical connecting plates alpha and beta, each of surface area S are charged minus q and q. Look at this. This is the minus q and this is the q. Okay. This is the alpha and this is the beta. Okay, no problem. A third identical plate gamma free to move is located on the other side of the plate with charge q at a distance t. Look at this. This is the charge gamma and charge q at this point. Okay. The third plate is released and collides with the plate B. Assume that the collision is elastic. The time of collision is sufficient to distribute the charge between beta and gamma. Okay. Now find the now, now question number 1, find the electric field acting on the plate gamma before collision. Look at this. The electric field due to this q charge is equal to q by 2 epsilon naught into s. And this field is directed along this direction. Now electric field due to minus q charge, this is the q divided by 2 epsilon naught s and this field directed along this direction. So net electric field towards the beta is equal to q minus q divided by 2 epsilon naught s is the electric field towards the this direction. Okay. Now question number B, find the charge on B. Now charge on beta and gamma after collision. Look at this. When collision occurs, the charge on beta and gamma, look at this, as they are in contact. So look at this electric field between at any point within the conductor is 0. So look at this, the total charge 2q. The charge on gamma, this is the q1. So charge on beta is 2q minus q1. Okay. Now consider the field at the point P. The field inside the conductor is 0. So 0 equal to, look at this, this negative charge produces a field along this direction. This q1 charge produces a field along this direction and this q charge produces a field along this direction. Okay. So look at this, the field due to, look at the field due to 2q minus q. So this is the 2q minus q1 by 2 epsilon naught s minus, this is the, look at this, q1 plus minus q divided by q1 plus q2 divided by 2 epsilon naught s equal to 0. So look at this, 2q minus q1 equal to, this is the q1 plus capital Q. Okay. So look at this is the 2q minus q equals to 2q1. So q1 equals to 2q minus q by 2. Okay. So charge on gamma is the 2q minus q by 2. And charge on beta, look at this, charge on beta, this is the 2q minus q1. So look at this, This is the 2q minus 2q by q1 by 2. So look at this, the charge becomes 2q plus q by 2. Okay, no problem. Here, so look at this, here q1 equal to, this is the q minus q by 2, and q2 equal to q plus q by 2 with a charge on beta and gamma. Okay. Now find the velocity of the plate gamma after the collision and at a distance d from the plate. So look at this, if v be the velocity of the plate gamma, then half mv square, this equal to work done against the round trip. Now during forward motion, force is F1 into D, and during reverse motion, this is the F2 into D. Now before collision, work done equals to, look at this, the field becomes, this is the Q minus Q by 2 epsilon naught A into charge Q into D. No problem. Now during reverse journey, the field becomes, look at this minus q by 2. So q minus q by 2. So q minus q by 2 divided by 2 epsilon naught into charge on it. Now charge becomes, this is the q minus q naught by 2 whole square. So this into d. Now simplifying this equation, we can calculate velocity of the plane. Okay. Now look at this question number 130. Two charges minus q each are fixed separated by a distance 2d. A third charge q of mass m placed at midpoint and displaced slightly x perpendicular to the line joining the two fixed charges as shown in figure. So look at this distance is x. This is the d. Now x is very small d. So look at this, q experiences a force along this direction. What is the force? Force, suppose this is the F1. Now Q also experiences a force along this direction. Okay, this is also F1. Now if this angle theta, the resultant force is directed along this direction. So look at this, the resultant force, this is the negative sign of 2 F1 cos theta. Negative sign means force directed towards the midpoint. Now look at this. What is the force? Look at this, 2 into, this is the q square divided by, this is the 4 pi epsilon naught, and this is the d square plus x square. And cos theta, look at this, cos theta is the x by root under of, this is the d square plus x square. So look at this is the negative side. So force F equal to, this is the 2q square x divided by 4 pi epsilon naught, this is the d square plus x square to the power 3 by 2. As x very small in comparison to d, so this term can be replaced by dq. So look at this, f equal to negative sign of, this is the 2q square x divided by 4 pi epsilon naught, this is the dq. Look at this force is the, look at this, f directly proportional to minus x, so it is ACHM. Now if omega be the angular frequency, then m omega square x, this equal to minus 2q square x divided by, this is the 4 pi epsilon naught dq. This and this cancel out. So omega equal to, look at this is the q square by 2 pi epsilon naught m dq. Okay, so what is the period? Look at this, period t equals to 2 pi by omega. So look at this is the 2 pi into 2 pi into 2 pi epsilon naught m d cube divided by q square to the power half is the time period of oscillation. Okay, look at this. This is the last question. Question number 1.31. A total charge minus q is uniformly spread along the length of a ring of radius r. Look at this. This is a ring of radius r. Okay. Now charge is minus q here. Suppose a very small charge dq at this point. So this is the dq. Now now a small test charge plus q of mass m is kept at the center on the ring and is given a gentle push along the axis of the ring. Due to gentle push, suppose it moves by distance x. X is very small in comparison to the radius of the ring. So this is the r. Okay, no problem. This is the r. So distance from dq. So distance of charge q from the dq. This is the root under of this is the r square plus x square. So force df. So force df equal to this is the dq into q divided by 4 pi epsilon naught into this is the r square plus x square. Okay. Now net force, look at this df dash. This equal to df cos theta. Cos theta is equal to x by root under of this. So look at this. This is the dq into q divided by 4 pi epsilon naught, and cos theta is the x by root under r square plus x square. So this is the x by root under of r square plus x square. This is the cube. So this is the 3 by 2. Okay, no problem. Now, so net force along the axis, this equal to this is the total charge q into qx divided by 4 pi epsilon naught, and this is the r cube, as x is very small compared to capital R. As this force is direct towards the center, so this is the negative side. So here look at this F proportionate minus x. So it is SHM. It omega be the angular frequency. So m omega square x with negative sign equal to minus capital Q small q x divided by 4 pi epsilon naught r cube. Therefore, look at this omega equal to this is the root under of capital Q small q 4 pi epsilon naught m r cube. Okay, so its period t equal to this is the 2 pi by omega. So look at this 2 pi. This is the root under of this is the 4 pi epsilon naught m r cube whole divided by capital Q and small q. Okay, many thanks for watching this video. This video will be extremely helpful for your preparation in 10+2 main, NEET and advanced. Hope you understand this. Please like, share, comment on this, and don't forget to subscribe my channel to get the new videos for your preparation in best level.